Okay, now let's go do about the control system design for the each of the term conditions. So this is the first term condition. So we'll be doing here LQR control on both latitude and longitude. So once we get the A and A lat and A long matrices and the term states, we first initialize the commanded longitude values and latitude values. So just basically this. So if you notice, for the first two term conditions, we'll control 5 states in the longitude, including the altitude. But in the last term condition, you would neglect this. So we'll talk about that later. So again, we are interested in controlling only the first 5 states in A long matrices, which is delta U, W, Q, delta theta, and PZ, and 4 states in lateral, which is V, P, R, and delta phi. So we'll scrape out those states from the A long and A lat matrices. If you recollect, A long and A lat are each 6x6 matrices respectively. So, but we would be needing only the first 5 states from A long and only the first 4 states from A lat. So we take this value. So this is arbitrary. So we take these two sets of matrices for A long and A lat. So the Q and R matrices, and we go on to the LQR. So and we get the A long L matrices. So first see how this works on the linear model. So if you see for the latitude, all the values use P, V, P, R, phi, and C. All the values are in the order of 10 to the minus 7. So it's expected because we are traveling in a straight line, so we don't have any side slips. So all these values are set to 0 or almost 0. You'll see the longitudinal curve now. And this is also expected. So when traveling in a straight line, most of the components should be along the body fixed x-axis, which is the velocity u. So we have that, and we'll see the altitude settling to somewhere close to minus 100. It's not actually 100. We have some steady state error, maybe of like 5 meters. So this is because we don't have an integral control here. We only have proportional control. So the steady state error is prone to occur. And all the other values settle to 0 or somewhat close to 0. So now let's see how this design fares in the nonlinear model. We'll go about simulate this in nonlinear model. So again, this is the nonlinear model, and this is the control system design we have done. So we have a little disturbance from the events and the gust here, so that is going to the system. So from the states, again, we scrape out only those states that we need for controlling using the E lat and E long matrices. And this is the commanded latitude, and the commanded longitude. So we basically calculate the errors, feed into the respective gain matrices. And then and if you notice, all the control system design we are doing is only the deviation from the trim control input. So we need to add them. So that input comes from this block here. And then again we have saturation blocks that defines our limits. And then we send this, we mux them, the 4 inputs into one, and send as delta. Now let's see how it fares. So if you see there's a slight deviation and the slight drift along the y coordinate, and but the which is very less when compared to the movement along the x-axis. So we see the altitude and the velocity being maintained. So yeah. Okay, now we'll do the same thing for the second term condition. So these are the K long and K lat matrices. So again, we'll see how it works on the linear model. This is a longitudinal design. Expected behavior. So we have the same graph, or almost the same graph here. But what's going to vary is the longitudinal graph. So if you're making a turn, you need to have some roll rate which is there. The pitch rate, it reduces to 0. So we see psi, that is the heading angle, increasing, and phi, which is the roll angle, that settles to some value, and the roll rate drastically reduces to 0, and all the other components on the side and the slightly velocity is also to 0. So this works fairly in linear model. Let's see how it works on the non-linear model. So again, we have the same design here in the simulation. Let's see how it works. So we see the altitude and the velocity is being maintained. The system is taking a coordinated turn. The system is tracking the roll angle here. So it's a constant roll angle. So we can see that even with winds and gust, the system is able to track all set points. And the heating increases and then it starts from 0 again to 360 degrees. So that's about it.